Our next topic is potential energy of a spring. A spring, its normal length, a body of mass m block is attached to the spring. If a spring is stretched from its normal length by x, then a spring force is developed in the spring towards left side, opposite to the displacement. If a spring is compressed from the normal length, again a spring force is developed now towards right side. A spring force opposite to the displacement. In first figure, a spring is in normal length, so a spring force is 0. Extension or compression is also 0. Normal position, normal means equilibrium of the spring mass system here. In second figure, the spring force is negative and displacement x is positive. And in third figure, the spring force is towards right, that is positive, and displacement x is negative. So if we show the graph of spring force with respect to extension and compression, then it is found to be a straight line. This is y-axis with respect to the equilibrium position, x-axis compression and extension we are showing on x-axis. X is the extension in the normal length and minus x compression in the normal length. The spring force is directly proportional to negative of the displacement minus x, or it is equal to minus kx, and this relation is called Hooke's law. So, whenever there two quantities are directly proportional, the graph is a straight line, and in Hooke's law k is called a spring constant. So the spring constant versus x graph is a straight line passing through the origin. When x is positive, force is negative, and when x is negative, force is positive, right? So work done by spring force in stretching the spring can be calculated by integration. As you see, the spring force is a variable force. So work done by variable force is calculated by integration, limits 0 to x, and spring force is minus kx. So integration of minus kx dx, k is spring constant, integration is with respect to x, so integration of x dx is x square by 2, limits 0 to x, and after putting the limits, this is minus kx square by 2, right? And the same work done in stretching the spring can be obtained by calculating the area under the spring force versus displacement graph. Area of the shaded region also gives the work done in stretching the area of shaded triangle, right? And this is equal to half base into altitude. Altitude is force here, force which is equal to minus kx. So this is also half kx square. So work done in stretching the spring is equal to area under the force displacement graph, and work done can also be calculated by integration. Now work done by external pulling force. This we have calculated work done in stretching the spring, and same will be the work done in compressing the spring. X is negative, then force is positive. So same will be the work done. Area of this triangle now, when displacement is compression, displacement is negative, force is positive. So again area will be, work done will be minus half kx square, right? So now we discuss the work done by the external force in stretching the spring will be equal to plus half kx square. Work done by the spring force was minus half kx square, and same will be the work done in pulling the spring, in pulling the mass, or work done by the external force in stretching the spring, half kx square, positive half kx square. And this work done by the external force, we say that energy is stored in the spring, in stretched spring or in compressed spring. And this potential energy is elastic potential energy in the spring, which is equal to work done by the external pull. Potential energy of the spring is work done by the external pulling force in stretching the spring. Stretching the spring, that is half kx square. So this is the potential energy in a stretched spring or in a compressed spring. Energy is stored on both the sides, whether the spring is stretched or it is compressed, right? Now see, how does the potential energy change when a spring is stretched or compressed? This is equilibrium position when x 0. This is when spring is stretched by x positive, x negative. When spring is compressed on both the sides, potential energy increases, right? And if you see the formula of potential energy, half kx squared, whether spring is stretched or compressed. Now if spring is released, if mass is released after stretching, then its elastic potential energy changes into kinetic energy. So energy we are showing on y-axis. See the graph of kinetic energy. Kinetic energy is maximum at the mean position, at the equilibrium position, where potential energy is 0, kinetic energy is maximum. And the graph of total energy is the horizontal line. This graph is for total energy. Total remains conserved, right? Now we shall discuss that spring force is a conservative force. There are two properties of conservative forces. Number one, work done by the conservative force is path independent, and number two, work done by the conservative force in a round trip is 0. So both these properties are fulfilled by the spring force. If block attached to the spring is moved from initial displacement xi to final displacement xf, then the work done by the spring force is f dx, limits of integration xi to xf, and spring force is minus kx, right? Minus k constant, and integration of x dx is x square by 2, and limits are written on the right side of the bracket. And now substituting the limits, we have kxi square divided by 2 minus kxf square divided by 2, right? Now it is clear that the work done by the spring force depends only on end points. And second property, work done in a round trip is 0. That can be proved here. If block is pulled from displacement xi and returns to same displacement, then what is the work done? Work done by the spring force, again f dx, work done by the spring force, limits of integration of xi to xi in a round trip. F is minus kx, and now solving integration, we have minus k constant, and integration of x dx is x square by 2, limits xi to xi. Minus k xi square by 2 minus xi square by 2, this is 0. Now it is also proved that work done by the spring force in a closed path is 0, right?